Right now, as you watch this, trillions of invisible particles are streaming through your body, right through your hands, your eyes, even the screen in front of you, without leaving a single trace. They move like ghosts, passing effortlessly through planets, stars, and even you, as if the solid world around us doesn't exist at all. These are neutrinos, the universe's most mysterious travelers, and they hold the keys to secrets we're only beginning to uncover. Born in the fiery hearts of exploding stars and the aftermath of the Big Bang itself, neutrinos have been weaving through space and time for billions of years, quietly shaping the cosmos in ways we're just starting to understand. What makes these particles so fascinating isn't just their ability to move through matter untouched, it's the fact that they challenge everything we thought we knew about the universe. They're so tiny, so elusive, that for decades, scientists weren't even sure they existed at all. Yet without them, the stars wouldn't shine the way they do. The elements that make up our world might never have formed, and the very fabric of reality could be fundamentally different. Neutrinos are the universe's silent architects, working behind the scenes to hold everything together, and yet, we've only scratched the surface of their story. So how do we study something that refuses to be seen? Why do these ghostly particles behave in ways that defy the laws of physics as we know them? And what can they tell us about the origins of the cosmos, the fate of dying stars, or even the hidden dimensions of space itself? The answers lie in some of the most daring experiments ever conceived: deep underground labs, detectors buried in Antarctic ice, and observatories that watch for the faintest whispers of these cosmic phantoms. This is the story of the secret lives of neutrinos, and by the end of our journey, you'll never look at the empty space around you the same way again. Because the truth is, it's not empty at all. To understand where neutrinos come from, we have to look to the most extreme environments in the universe, places where matter is stretched, crushed, and transformed under forces beyond imagination. Take the heart of a star like our Sun, for example. Every second, deep in its core, hydrogen atoms smash together under unimaginable pressure, fusing into helium and releasing energy in the process. But that energy doesn't just come in the form of light. It also spawns countless neutrinos, tiny particles that zip away at nearly the speed of light, untouched by the dense plasma around them. In fact, trillions of these ghostly particles from the Sun pass through your fingernail every second, and you'd never even know it, but the Sun is just the beginning. When a massive star reaches the end of its life, it doesn't fade quietly. It explodes in a supernova, one of the most violent events in the cosmos. In that cataclysmic moment, as the star's core collapses, an unimaginable flood of neutrinos bursts outward, carrying away more energy than the star emitted in its entire lifetime. These particles are so efficient at escaping that they actually help trigger the explosion itself, acting like an invisible shockwave that blasts the outer layers of the star into space. Without neutrinos, some supernova might not even happen the way we see them. And then there are the rarest, most energetic neutrinos of all, the ones born in collisions between neutron stars or near supermassive black holes. These cosmic powerhouses accelerate particles to near-light speeds, creating ultra-high-energy neutrinos that can travel billions of light-years before reaching us. Even Earth's own atmosphere plays a role. When cosmic rays, high-energy particles from deep space, slam into air molecules, they shatter into showers of secondary particles, including neutrinos. That means every time you look up at the sky, you're standing beneath an invisible rain of particles from across the galaxy. So how do we detect something so fleeting? The answer lies in some of the most ingenious experiments ever devised. Deep underground, where Earth's crust shields detectors from other particles, scientists build vast chambers filled with ultra-pure water or liquid argon. When a neutrino, by sheer chance, collides with an atom inside, it creates a tiny flash of light or a burst of charged particles, a faint signal that researchers can trace back to its origin. Other detectors are buried in Antarctic ice or submerged in the ocean, turning entire landscapes into neutrino telescopes. It's like trying to catch a whisper in a hurricane, but when we succeed, the secrets these ghostly messengers carry are worth every effort. Imagine throwing a handful of sand at a chain link fence. Most grains would bounce right off, but a few might slip through the gaps. Now picture throwing trillions upon trillions of grains, and only one or two make it past. That's essentially what happens when neutrinos encounter matter. These particles don't just slip through the gaps in atoms, they barely notice atoms exist at all. While other particles like electrons or protons are constantly interacting with their surroundings through electromagnetic forces, neutrinos carry no electric charge. They're like cosmic shadows gliding through walls, planets, and even entire stars without leaving a trace. What makes them even stranger is their near weightlessness. For decades, scientists believed neutrinos had no mass at all, moving at the speed of light like tiny, invisible photons. But then came the bombshell discovery: neutrinos do have mass, just so infinitesimally small that it barely registers. A single neutrino is at least 1,000,000 times lighter than an electron, the next lightest particle we know. This featherweight quality means they're not just passing through matter, they're barely even nudging it as they go. Yet their ghostly behavior isn't just a quirk, it's a revolutionary clue. The fact that neutrinos have mass at all was the first crack in the seemingly perfect structure of the standard model of particle physics, the rulebook scientists have used for decades to explain how the universe works. Suddenly, we had proof that there's more to the story, that some of the universe's deepest secrets might be hiding in these silent travelers. Some theories suggest neutrinos could be connected to dark matter, the invisible glue holding galaxies together. Others speculate they might be slipping in and out of hidden dimensions, realms of space we can't yet perceive. And then there's the way they shape-shift. Neutrinos come in 3 known types: electron, muon, and tau. And as they travel, they don't stay in one form. They oscillate, morphing from one flavor to another in mid-flight, like a chameleon changing colors as it moves. This bizarre behavior was another shock to physicists, proving that neutrinos don't play by the usual rules. It's as if you tossed a red ball into the air and watched it turn blue, then green, before landing back in your hand. Catching these phantoms is like trying to trap fog with a fishing net. Even the most sophisticated detectors like Japan's Super-Kamiokande, a massive underground tank filled with 50,000 tons of ultra-pure water, only spot a fraction of the neutrinos passing through. The rest vanish without a trace, leaving behind just enough clues to keep scientists chasing after them. But every rare interaction, every flicker of light in a detector, carries information from across the cosmos, messages from the hearts of stars, the wreckage of supernova, and possibly even the birth of the universe itself. The universe loves a good mystery, and neutrinos deliver one of the strangest twists in particle physics: their ability to change identities mid-journey. Picture this: a neutrino leaves the Sun as an electron neutrino, the type produced in nuclear reactions. By the time it reaches Earth, just a few light minutes later, it might have transformed into a muon neutrino or even a tau neutrino. This isn't science fiction, it's a real phenomenon called neutrino oscillation, and it's as mind-bending as watching a cup of coffee spontaneously turn into tea, then into hot chocolate, all without anyone touching it. For years, scientists were stumped by a peculiar discrepancy. When they calculated how many electron neutrinos should be arriving from the Sun, their detectors kept coming up short. It wasn't a measurement error, it was a clue. The missing neutrinos weren't vanishing, they were disguising themselves as other flavors, slipping past instruments designed to spot only one type. This discovery didn't just solve a solar puzzle, it shattered a fundamental assumption about the universe. If neutrinos could oscillate, they couldn't be massless, as the standard model had long assumed. That tiny wobble in their identity meant they had to carry some weight, however minuscule. The revelation was so groundbreaking it earned the physicists behind it the Nobel Prize in 2002. So how does this quantum sleight of hand work? Think of each neutrino flavor not as a fixed identity, but as a mixture of three possible mass states. As the particle travels, these states evolve at slightly different rates, like musical notes drifting in and out of harmony. When they recombine, the result might be a different flavor than the one that started the journey. It's as if you left home wearing a red shirt, but by the time you reached your destination, the color had subtly shifted to blue, not because you changed clothes, but because the very fabric of your shirt was in flux. But here's where the plot thickens. Neutrino oscillation hints at physics beyond our current understanding. Some theories suggest undiscovered particles, sterile neutrinos, could be interacting with the three known flavors, nudging them into their strange dance. Others speculate that hidden dimensions curled up in the fabric of spacetime might be influencing their behavior. Every time researchers build a more sensitive detector, like the upcoming deep underground neutrino experiment, which will fire a beam of neutrinos 800 miles through Earth's crust, they're not just testing theories. They're hunting for ghosts that might rewrite the rules of reality. The implications ripple far beyond particle physics. If neutrinos can oscillate, what else might be possible? Could their tiny masses explain why the universe is made of matter rather than antimatter? Some scientists believe neutrino behavior might hold the key to one of cosmology's biggest questions: why we exist at all. Every time one of these phantoms flickers into view, it's not just a detection, it's a whisper from the universe, urging us to look deeper. And the more we listen, the more we realize how much we still have to learn. Catching a neutrino is like trying to photograph a shadow. You can't see it directly, but with the right tools, you can capture the faintest trace of its presence. That's where neutrino detectors come in, engineering marvels designed to do the impossible, trap the untrappable. Take Super-Kamiokande, and in Japan, a colossal stainless steel tank buried deep beneath a mountain, filled with 50,000 tons of water so pure it's like staring into a void. When a neutrino, by some cosmic fluke, collides with an atom in that water, it creates a fleeting burst of light called Cherenkov radiation, a blue glow that ripples outward like a whisper in the dark. Sensors lining the tank's walls catch that glow, turning a ghostly interaction into data scientists can study. But water isn't the only way to hunt these phantoms. In Antarctica, the IceCube detector turns an entire cubic kilometer of glacial ice into a neutrino telescope. When a high-energy neutrino smashes into an atom deep in the ice, it spawns a cascade of secondary particles, each leaving a trail of faint light as they zip through the frozen expanse. Thousands of sensors buried in the ice track these trails, mapping the neutrino's path back to its origin, sometimes to distant galaxies or cataclysmic cosmic events. It's astronomy, but instead of telescopes pointing at the sky is screaming its secrets into the ice beneath our feet. Then there's the Sudbury Neutrino Observatory in Canada, where scientists filled a massive acrylic sphere with heavy water infused with deuterium, a special form of hydrogen. When neutrinos interact with deuterium, they trigger reactions that reveal not just their presence but their flavor, helping solve the mystery of those missing solar neutrinos. And in Italy, the Borexino experiment uses a tank of liquid scintillator, a material that lights up like a firefly when a neutrino grazes it, offering clues about the nuclear furnace at the sun's core. But why go to such extremes? Why build these underground cathedrals of science, waiting years just to catch a handful of interactions? Because neutrinos are cosmic messengers, carrying stories from places we can't otherwise see. When a star explodes, light can take centuries to escape the debris, but neutrinos rush out in seconds, giving us a real-time alert to the universe's most violent events. They might even hold clues to dark matter, or reveal why the universe favors matter over antimatter, a bias that allowed galaxies, planets, and us to exist at all. And the hunt is only getting more ambitious. The upcoming deep underground neutrino experiment will shoot a beam of neutrinos from Fermilab in Illinois to a detector in South Dakota, 800 miles away, watching how they morph along the journey. It's like sending a letter through a maze and studying how the words change by the time it arrives. Every flicker of light in these detectors, every rare collision, is a piece of a puzzle we're still assembling, one that could rewrite our understanding of reality itself. Every second, the Sun bombards Earth with 60 billion neutrinos for every square centimeter of surface, enough that trillions pass through your body in the time it takes to blink. But here's the puzzle that kept scientists awake at night for decades. When early detectors like the Homestake experiment in South Dakota tried counting these solar neutrinos, they kept coming up short. The numbers didn't add up. Either our understanding of how stars work was fundamentally wrong, or something bizarre was happening to these particles on their journey through space. The answer turned out to be stranger than fiction. Neutrinos weren't disappearing, they were shape-shifting. As they raced toward Earth, some electron neutrinos born in the Sun's core were transforming into muon and tau neutrinos, flavors that early detectors couldn't see. This chameleon-like behavior, confirmed by later experiments like Sudbury Neutrino Observatory, didn't just solve the solar neutrino problem, it handed scientists a Rosetta Stone for decoding stellar engines. For the first time, we had direct proof that the Sun's energy comes from nuclear fusion, the same process we've tried to replicate here on Earth. But solar neutrinos do more than validate textbooks, they're live feeds from the heart of a star. Unlike light, which can take 100,000 years to struggle through the Sun's dense layers, neutrinos zip straight out from the core in seconds. By studying their energy spectra, we can essentially take the Sun's temperature, monitoring shifts in fusion reactions in real time. When a detector like Italy's Borexino catches these particles, it's like placing a stethoscope against the Sun's fiery chest, listening to the rhythmic pulse of protons fusing into helium. Now imagine harnessing these cosmic messengers as early warning systems. Some researchers speculate that changes in solar neutrino fluxes could signal impending solar storms, those violent eruptions that threaten satellites and power grids. Even more tantalizing, neutrinos from a dying star arrive hours before its light does. If a nearby star went supernova, detectors like Super-Kamiokande would sense the neutrino surge almost instantly, giving astronomers precious time to point telescopes at the explosion's first moments. Yet for all we've learned, the Sun still holds mysteries. Why do certain neutrino measurements hint at unexpected energy patterns? Could there be a fourth, even more elusive neutrino type dancing just beyond our detection? Each unanswered question is a reminder. The universe's quietest particles often have the loudest things to say. When a massive star reaches the end of its life, it doesn't fade quietly. It unleashes a supernova, one of the most violent events in the cosmos. But what's truly astonishing isn't just the blinding flash of light or the shockwaves rippling through space. It's the invisible tsunami of neutrinos that floods outward, carrying away 99% of the star's energy in a single, staggering pulse. For a brief moment, the dying star becomes the brightest neutrino source in the universe, outshining entire galaxies in these ghostly particles. Take the supernova of 1987, for example. Hours before telescopes caught the first glimmer of light from the explosion, neutrino detectors on Earth picked up a sudden spike: 24 particles in less than 15 seconds. It might not sound like much, but for scientists it was a revelation. Those neutrinos had raced ahead of the light, slipping effortlessly through the star's collapsing layers while photons struggled to escape. That tiny flicker in the data wasn't just a detection. It was a live broadcast from the heart of a dying star, proof that neutrinos could serve as cosmic alarm bells. But why do supernovae dump almost all their energy into these invisible particles? The answer lies in the chaos of a collapsing core. As the star's inner layers implode under gravity, protons and electrons are crushed together so violently they merge into neutrons, releasing a flood of neutrinos in the process. These particles don't stick around, they surge outward at nearly the speed of light, acting like an invisible shockwave that helps blast the star's outer layers into space. Without neutrinos, some supernova might fizzle out instead of exploding, leaving behind a quiet neutron star rather than scattering stardust across the cosmos. And that stardust holds the key to something even more remarkable: the origins of the elements that make up our world. The extreme conditions in a supernova forge heavy atoms like gold, platinum, and uranium, elements too complex to form in ordinary stars. Neutrinos play a surprising role here too. As they stream outward, they interact with the swirling debris, transforming nuclei like alchemists turning lead into gold. In fact, some of the gold in your jewelry might owe its existence to a neutrino's fleeting touch during a stellar explosion billions of years ago. Now imagine if a nearby star, say, Betelgeuse, went supernova tomorrow. The light would be dazzling, visible even in daylight, but the real show would happen underground. Detectors worldwide would light up with trillions of neutrinos, offering a front-row seat to the explosion's inner workings. Scientists could track the core's collapse in real time, watch elements form, and maybe even spot hints of exotic physics we've never seen before. It would be like receiving a telegram from the universe itself, written in particles that barely interact with anything, yet carry the loudest stories of all. The question isn't just whether we're ready for the next supernova neutrino blast, it's how much we're willing to listen. Every one of these ghostly messengers is a time capsule from the edge of physics, holding secrets about how stars live, die, and seed the universe with the ingredients for planets, life, and everything in between. And the next cosmic broadcast could arrive at any moment. All we have to do is keep watching the dark. Right after the Big Bang, when the universe was just a seething, trillion-degree soup of energy, neutrinos ruled the cosmos. Picture this: for the first second of existence, these ghostly particles outnumbered atoms by over 1 billion to 1, flooding space like an invisible ocean. As the newborn universe expanded and cooled, neutrinos were among the first particles to break free from the chaos, streaming outward unimpeded while other matter still clumped together in a thick plasma. This cosmic decoupling happened so early, just 1 second after creation, that if you could rewind time, you'd see neutrinos flying free while the rest of the universe was still too hot to form even the simplest atoms. These primordial neutrinos didn't just witness the universe's infancy, they helped sculpt it. As they raced outward at near light speed, their collective gravity subtly tugged on denser regions of matter, like invisible hands kneading dough. This gentle pulling may have guided where the first galaxies eventually formed, leaving faint fingerprints on the large-scale structure of everything we see today. It's a staggering thought. The same particles now passing through your body helped weave the cosmic web billions of years before Earth existed. And here's the mind-blowing part: those ancient neutrinos are still around. The universe has stretched 100,000 times over since their release, cooling them to mere whispers of their original energy. Today, they drift through space at nearly the speed of light, but with so little vigor that a single solar neutrino carries millions of times more energy. Scientists estimate there are about 300 of these relic neutrinos in every cubic centimeter of space, a faint echo of creation hiding in plain sight. The problem: detecting them is like trying to hear a feather land in a hurricane. Current technology can spot high-energy neutrinos from stars or supernova, but Big Bang neutrinos are so lethargic they barely interact with matter at all. To catch one, we'd need a detector the size of a planet, chilled to near absolute zero, with walls so dense they could trap particles that normally pass through light years of lead. Yet the payoff would be unparalleled: a direct line to the universe's first moments, like finding a perfectly preserved fossil from the dawn of time. That hasn't stopped physicists from dreaming up audacious solutions. Some propose using quantum sensors so precise they could spot the infinitesimal jiggle a relic neutrino imparts on an atomic nucleus. Others imagine exploiting rare interactions in ultra-cold materials, where even the faintest nudge from a 14-billion-year-old particle might leave a trace. The challenge isn't just technical, it's a race against the universe's expansion. As space stretches, these neutrinos lose even more energy, fading further into obscurity with every passing eon. Why go to such extremes? Because hidden in those ghostly particles could be answers to cosmology's biggest riddles. Did neutrinos tip the scales in matter's favor over antimatter? Do they hold clues about dark energy or the universe's ultimate fate? Every undetected relic neutrino is a postcard from the Big Bang, waiting to be read. And if we ever learn to decode them, we won't just be studying history, we'll be touching it. The universe is filled with shadows, some we can see, like the silhouette of a galaxy against the void, and others that remain utterly invisible, their presence felt only by the way they tug on the fabric of space itself. Dark matter is the most famous of these cosmic phantoms, outweighing all the stars, planets, and nebulae combined by a factor of 5. But here's where things get even stranger. Could the same particles that pass through us like ghost neutrinos hold the key to unraveling dark matter's mystery? At first glance, the idea seems far-fetched. Regular neutrinos are far too light to account for dark matter's gravitational grip. A single neutrino's mass is less than a millionth of an electron's, making them practically weightless in the grand scheme of the cosmos. But what if there's another kind of neutrino, one we haven't yet detected? Enter sterile neutrinos, hypothetical heavyweights that could be the missing piece of the puzzle. Unlike their ordinary cousins, sterile neutrinos wouldn't interact through the weak nuclear force, the usual handshake of particle physics. They'd be loners, feeling only gravity's faint pull, slipping through the universe like whispers in an empty room. This is where the plot thickens. If sterile neutrinos exist, their sheer mass, potentially thousands of times heavier than regular neutrinos, could make them the perfect dark matter candidate. Picture a cosmic game of hide and seek where these particles form invisible scaffolding, their collective gravity sculpting galaxies into the vast webs we observe today. Some theories even suggest sterile neutrinos could decay into bursts of X-rays, leaving behind faint fingerprints in the light of distant galaxy clusters. In fact, when astronomers spotted an unexplained X-ray signal from the Perseus cluster, some wondered, was this the signature of sterile neutrinos at last? The hunt is on. Experiments like Mini Bueni at Fermilab are firing beams of neutrinos through detectors, watching for anomalies that might hint at these elusive heavyweights. Meanwhile, underground labs are scouring for any flicker of interaction that defies the standard model's predictions. The stakes couldn't be higher. If sterile neutrinos are real, they wouldn't just solve the dark matter riddle, they'd tear open the rulebook of particle physics, revealing a hidden layer of reality we've barely glimpsed. Yet the mystery runs deeper. Even if sterile neutrinos aren't the sole architects of dark matter, they might still play a role in its story. Some models propose a cosmic alliance where multiple dark matter particles, some sterile, some entirely unknown, work together to shape the universe. It's like discovering that the shadows we've been chasing aren't cast by a single figure, but by an entire unseen crowd. The search for these ghostly particles is more than a scientific quest, it's a journey to the edges of what we know. Every experiment, every flicker of data, brings us closer to answering one of physics' most haunting questions. What is the universe really made of? And with each step forward, we're reminded that the darkest corners of space might be hiding the brightest revelations. In 2011, physics was turned upside down by a single, electrifying announcement: neutrinos might be breaking the ultimate cosmic speed limit. The Opera experiment in Italy had clocked these particles arriving 60 nanoseconds faster than light could travel the same distance. That's a fraction of a blink, but in the world of relativity, where Einstein's laws have reigned unchallenged for a century, it was like throwing a grenade into the foundations of physics. Headlines screamed about time travel and overturned theories, while scientists scrambled to make sense of the impossible. Then came the twist. The anomaly wasn't a glimpse of new physics, it was a loose fiber optic cable. A connection slightly out of place had skewed the timing measurements, turning what could have been a revolution into a humbling lesson in experimental precision. But here's the thing, even in failure, the Opera incident revealed something profound about our quest to understand neutrinos. These particles are so elusive, so indifferent to the usual rules, that when something seems off, it's worth asking whether we're seeing an error or the edge of a paradigm shift. What if neutrinos do have secrets about spacetime that we're only beginning to uncover? While they don't break light speed, they come tantalizingly close, and some theories suggest they might interact with space in ways we haven't yet imagined. Extra dimensions, warped spacetime, quantum foam, neutrinos could be threading through hidden layers of reality, their subtle deviations hinting at realms beyond our perception. Experiments like Minos and Icarus have since tightened the limits, confirming neutrinos respect light speed, but the door isn't entirely closed. Consider this: when a neutrino oscillates from one flavor to another, does it take the shortest path through space-time, or could it be flickering through dimensions we can't see? Some models propose that sterile neutrinos, those hypothetical heavy cousins, might shortcut through extraspatial folds, appearing to move faster without technically violating relativity. It's like watching a bug crawl across a folded napkin. From our perspective, it might seem to teleport, but in reality, it's just taking a hidden route. The beauty of neutrino research isn't just in the answers, it's in the questions that force us to rethink reality. Every time we build a more precise detector or design a cleverer experiment, we're not just testing particles, we're stress testing the universe's rulebook. And if history's any guide, neutrinos will keep surprising us. After all, what's the fun in studying ghosts if they don't keep you guessing? Black holes are the universe's ultimate vaults, locking away anything that crosses their event horizons, even light itself. But what if there's a cosmic messenger that can slip through their grip? enter neutrinos, the ghost particles that might just hold the keys to these gravitational monsters. Picture the violent chaos around a feeding black hole, where superheated gas spirals into oblivion in an accretion disk hotter than a million suns. In that maelstrom, protons collide with such fury that they shatter into sprays of particles, including neutrinos. These tiny escape artists don't just flee the disk, they rocket away at nearly light speed, untouched by the black hole's pull, carrying encoded details about the environment they left behind. Scientists believe these neutrinos could be cosmic spies, revealing secrets no telescope can see. The energy spectrum of neutrinos escaping an accretion disk, for example, might betray a black hole's spin, a property that warps spacetime itself. A rapidly rotating black hole drags the surrounding space like a whirlpool, and neutrinos born in its disk would bear the imprint of that motion. It's like tossing a handful of confetti into a tornado. How the pieces fly out can tell you how fast the storm is spinning. Then there's Hawking radiation, the eerie quantum effect that causes black holes to slowly evaporate. According to theory, pairs of particles and antiparticles flicker into existence at the edge of an event horizon. Normally, one falls in while the other escapes, stealing a tiny bit of the black hole's mass. But here's the twist. Some models suggest these escaping particles could include neutrinos, faint signals of a black hole's slow demise. Detecting them would be like catching whispers from the grave evidence of a black hole's final moments, long after it's vanished from view. But the real magic lies in what neutrinos might tell us about spacetime's fabric. When a black hole merges with another, the collision sends ripples through the universe's gravitational waves we can now detect. Yet hidden in the chaos could be bursts of high-energy neutrinos, created as shockwaves accelerate particles to unimaginable speeds. If we catch these neutrinos alongside gravitational waves, it would be like seeing a cosmic explosion in both sound and color, offering a multidimensional view of the violence. The challenge: black hole neutrinos are needles in a haystack of cosmic noise. Distinguishing them from the trillions of other neutrinos passing through Earth requires detectors with unprecedented precision. Projects like the planned Pacific Ocean Neutrino Experiment aim to turn entire ocean volumes into neutrino telescopes, listening for the faint clicks of particles that might have skirted a black hole's edge. And the implications go beyond mere observation. If neutrinos really can escape black holes, they might carry traces of physics beyond Einstein's theories, hints of quantum gravity or extra dimensions. Every neutrino that reaches us from the brink of an event horizon is a cipher waiting to be cracked, a message from a place where the laws of physics as we know them break down. The universe has spent billions of years hiding its deepest secrets inside black holes. Now we're learning their whispers might have been traveling to us all along, carried by the most elusive particles in existence. For centuries, astronomers have studied the universe by collecting light visible, infrared, X-rays painting pictures of the cosmos one wavelength at a time. But light has limits. It gets absorbed by dust, bent by gravity, or lost in the glare of brighter objects. Now imagine a telescope that doesn't rely on light at all, one that sees through cosmic obstacles like they're not even there. That's the revolutionary promise of neutrino astronomy, a field that doesn't just observe the universe but peers straight through its veil. The breakthrough came in 2017, when the IceCube detector buried in Antarctic ice caught a single, impossibly energetic neutrino. Unlike the trillions of solar neutrinos passing harmlessly through Earth every second, this one packed a punch equivalent to a major league fastball, all concentrated in a particle lighter than a billionth of a grain of sand. Tracing its path backward led scientists to something extraordinary. A blazar 4 billion light-years away, a supermassive black hole spearing the cosmos with jets of plasma moving at nearly light speed. For the first time, we'd pinpointed a neutrino's origin outside our galaxy, proving these particles could serve as cosmic breadcrumbs leading us to the universe's most violent engines. What makes neutrinos such powerful cosmic messengers is their refusal to play by light's rules. Take active galactic nuclei, the monstrous black holes at the center of galaxies, devouring matter and belching radiation. The regions around these black holes are so dense with gas and magnetic fields that even X-rays struggle to escape. But neutrinos, they sail right through, carrying unfiltered details about the particle acceleration happening near the event horizon. It's like trying to study a hurricane by listening to the wind versus having a probe embedded in the storm's eye. Neutrinos give us that insider's view, revealing processes hidden to traditional telescopes. And it's not just blazars. Neutrinos might hold the key to unraveling mysteries like gamma-ray bursts, the universe's most powerful explosions. These fleeting flashes of high-energy light could be the birth cries of black holes or collisions of neutron stars, but their inner workings remain opaque. If detectors catch neutrinos coinciding with a burst, it would be like finding a fingerprint at a crime scene, linking the explosion to specific particle interactions. Some theories even suggest neutrinos might arrive before the gamma rays, giving astronomers precious seconds to point telescopes at the right patch of sky. The real magic happens when we combine neutrino data with other cosmic signals, an approach called multi-messenger astronomy. Picture this: gravitational waves ripple through Earth, signaling colliding black holes. Seconds later, a neutrino detector picks up a matching burst while optical telescopes spot a faint afterglow. Suddenly, we're not just observing an event, we're experiencing it through sight, sound, and touch, metaphorically speaking. This convergence of signals could crack open questions about dark matter, quantum gravity, or why the universe favors matter over antimatter. Future neutrino telescopes promise even grander visions. Projects like KM3NET in the Mediterranean aim to turn entire ocean depths into detectors, while space-based concepts imagine using the moon as a neutrino sensor. Imagine mapping the cosmic web not by the glow of galaxies but by the neutrino rivers flowing between them, a shadow atlas of the universe's hidden architecture. We're witnessing the birth of an entirely new way to explore reality. Every neutrino that reaches us is a telegram from the universe's most extreme frontiers, written in a language we're just beginning to decode. And as our detectors grow more sensitive, we might find these ghostly particles have been telling stories all along. We just needed to learn how to listen. Deep beneath the concrete and steel of nuclear power plants, an invisible storm rages not of radiation, but of ghostly particles born from the heart of human engineering. Every second, as uranium atoms split in the controlled chaos of fission, they release more than just energy. They unleash a flood of electron antineutrinos, trillions upon trillions streaming outward like an atomic breath. A single reactor can produce more neutrinos in a day than all the stars in our galaxy combined, turning these man-made facilities into the most intense neutrino sources on Earth. For physicists, nuclear reactors aren't just power generators, they're laboratories. Unlike solar neutrinos, which arrive with a mix of energies shaped by the sun's complex fusion processes, reactor neutrinos emerge with a predictable energy spectrum, making them perfect calibration tools. Detectors like Daya Bay in China and Reno in South Korea sit within whispering distance of reactor cores, using these artificial neutrino beams to measure oscillation parameters with razor precision. It's like tuning a piano using a perfectly pitched note. The controlled environment strips away cosmic variables, letting scientists isolate the quirks of neutrino behavior. But reactors have also handed physicists a head-scratcher known as the reactor anomaly. When researchers tallied up the expected neutrino output based on fission physics, their detectors consistently came up short by about 6%. That missing fraction might seem small, but in particle physics, gaps like these often hide revolutions. Could the discrepancy point to sterile neutrinos, those hypothetical heavy siblings that evade detection entirely? Or does it reveal flaws in our models of nuclear decay? The debate rages, with experiments like Prospect at Oak Ridge National Laboratory hunting for answers in the precise energy patterns of reactor neutrinos. Meanwhile, these ghostly particles are quietly revolutionizing nuclear security. Since antineutrinos escape reactors unimpeded, their flux provides a real-time window into a core's activity. Detectors positioned near facilities can monitor changes in neutrino output, instantly flagging if fuel is diverted for weapons production, a technology already deployed in projects like IAEA safeguard programs. It's nuclear non-proliferation with a particle physics twist, invisible sentinels standing guard against invisible threats, yet the story doesn't end there. Some reactors are now being repurposed as neutrino sources for fundamental research. Canada's Darlington plant will soon host the SNO+ experiment, using its neutrino stream to probe why matter dominates over antimatter in the universe. Others aim to study how neutrinos interact with atomic nuclei, data crucial for designing next-generation reactors or even spotting clandestine nuclear tests. From unraveling quantum mysteries to policing global security, reactor neutrinos prove that humanity's most controversial energy source has become an unexpected ally in decoding the universe. And with every flicker of light in a detector, we're reminded, even our inventions can't escape the ghostly touch of these cosmic phantoms. Beneath our feet, in the crushing depths where Earth's mantle churns like molten glass, a hidden nuclear furnace quietly powers the planet. Uranium, thorium, and potassium isotopes decay in this scorching darkness, their atomic transformations releasing not just heat, but geoneutrinos, ghostly fingerprints of Earth's radioactive heart. These particles emerge straight from the rock itself, streaming upward through thousands of miles of solid stone as effortlessly as sunlight through a window. For geologists, every geoneutrino that reaches the surface is a telegram from places we can never drill, mapping the distribution of radioactive elements with a clarity no seismic wave could match. The first confirmed detection came from Japan's Camland detector in 2005, a triumph of patience and precision. Nestled in a mine shielded from cosmic rays, the experiment's liquid scintillator caught the faint blue flashes of antineutrinos interacting with protons, particles born not from stars or reactors, but from Earth's own uranium and thorium. The data revealed something startling. About half of our planet's internal heat comes from radioactive decay, solving a century-old debate about what keeps Earth's engine running. The rest likely dates back to the planet's violent formation, residual warmth from the primordial collisions that built our world. Now imagine using these ghostly messengers to peer deeper. Geoneutrinos could trace mantle plumes, those colossal upwellings of hot rock that fuel volcanic chains like Hawaii. By comparing detection rates at different locations, scientists might reconstruct hidden reservoirs of radioactive material, effectively creating an X-ray of Earth's interior. Future detectors placed on opposite sides of tectonic plates could even track the slow dance of subduction, watching as one slab of crust dives beneath another, carrying its geoneutrino signature into the abyss. The implications ripple beyond pure science. Geoneutrinos might pinpoint untapped uranium deposits without a single drill hole, guiding mineral exploration with minimal environmental impact. They could also monitor nuclear non-proliferation. Natural Geoneutrino backgrounds provide a baseline, making it harder to conceal illicit reactors. Projects like SNO Plus in Canada and Jinping in China are already refining these techniques, turning entire continents into neutrino telescopes aimed inward at our own planet. Yet the grandest promise lies in solving Earth's energy budget, calculating exactly how much heat drives earthquakes, volcanoes, and continental drift. Some models suggest we're missing a portion of the planet's radioactivity, perhaps concealed in the core or locked in minerals we've yet to identify. Others speculate that Geoneutrinos might reveal exotic particles or unknown nuclear processes at work in Earth's depths. Every flicker of light in these detectors isn't just data, it's a whisper from the underworld, reminding us that the ground beneath our feet is alive with atomic fire, and we're only beginning to understand its language. In the strange world of quantum physics, where particles can be in two places at once and vanish in one spot only to reappear in another, neutrinos might pull off their most baffling trick yet, moving backward through time. The idea sounds ripped from science fiction, but some theories suggest these ghostly particles could be flipping the arrow of time, appearing to us as their own antimatter opposites. This isn't just a wild speculation, it's tied to a hypothesis proposed by physicist Eta Majorana nearly a century ago. He theorized that certain particles, now called Majorana fermions, could be their own antiparticles, a property that would make neutrinos cosmic time travelers of sorts. Picture a neutrino born in the heart of a supernova. According to conventional physics, it zips forward through time, racing toward Earth at nearly light speed. But if Majorana was right, that same neutrino might also be its own antineutrino, a particle moving backward in time from our perspective. It's as if the universe handed neutrinos a quantum hall pass, letting them bend the rules of cause and effect. This bizarre behavior isn't just a curiosity. It could solve one of cosmology's biggest mysteries, why the universe is filled with matter instead of antimatter. Here's the puzzle. The Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other on contact, leaving behind a lifeless sea of energy. Yet here we are in a cosmos dominated by matter stars, planets, and us. Neutrinos might hold the key. If they truly are Majorana particles, their time-flipping antics could have tipped the scales in matter's favor during the universe's earliest moments. Every time a neutrino oscillated between flavors while moving backward in time, it might have subtly favored the creation of matter over antimatter, seeding the cosmos with the stuff that would eventually build galaxies. Scientists are hunting for proof in the most delicate experiments imaginable. Take Core, a detector buried under a mountain in Italy, chilled to near absolute zero to catch an ultra-rare nuclear decay called neutrinoless double beta decay. If observed, this decay would mean two neutrons in an atomic nucleus turned into protons without emitting the expected antineutrinos, strong evidence that neutrinos are their own antiparticles. It's like watching a magic trick where the magician's assistant disappears without a trace, leaving only the faintest clue that the laws of physics just got rewritten. The implications stretch far beyond particle physics. If neutrinos really are time-traveling Majorana particles, they might be weaving the fabric of reality itself, stitching together moments across billions of years. Every oscillation, every flavor change could be a tiny stitch in the cosmic tapestry, ensuring the universe didn't vanish into pure energy before life had a chance to emerge. The search for these quantum loopholes isn't just about understanding neutrinos, it's about uncovering the hidden architecture of existence, one ghostly particle at a time. Buried beneath the endless white expanse of Antarctica, where temperatures plunge to negative 100 degrees Fahrenheit and the sun vanishes for months at a time, lies one of the most audacious experiments in human history, the IceCube Neutrino Observatory. This isn't your typical telescope pointed at the stars. Instead, it turns an entire cubic kilometer of ancient glacial ice into a colossal particle detector, a frozen net cast into the cosmos to snare the universe's most elusive messengers. The brilliance of IceCube lies in its simplicity. Over 5,000 basketball-sized sensors, strung like beads on vertical cables, are buried deep beneath the ice sheet, forming a grid that spans from 1,400 to 2,500 meters below the surface. When a high-energy neutrino, often traveling from billions of light-years away, finally collides with an atomic nucleus in the ice, the impact spawns a secondary particle called a muon. This muon streaks through the ice faster than light can travel in that medium, creating a shockwave of blue Cherenkov radiation, a faint glow that pulses outward in a cone-shaped pattern. The sensors catch that glow, tracing the particle's path back to its origin with astonishing precision. It's like capturing the ripple of a pebble dropped in a dark pond. Only the pond is a slab of ice older than human civilization, and the pebble came from the heart of a distant galaxy. But why bury this detector under a polar wasteland? Antarctica's ice is nature's perfect shield. Miles of dense, ultra-pure glacial ice filter out cosmic rays and other background noise that would overwhelm detectors on the surface. The darkness at those depths is absolute, allowing even the faintest Cherenkov flashes to stand out like fireworks in a blackout. And the ice itself acts as both detector and lens. Its crystalline structure preserves the light trails with minimal distortion, letting scientists reconstruct a neutrino's journey down to the angle of its arrival. The payoff has been revolutionary. In 2013, IceCube announced the first detection of neutrinos from outside our galaxy particles with energies 1,000,000 times greater than those produced in supernova. Dubbed Bert and Ernie by researchers, followed by a series of even more energetic detections nicknamed Big Bird, these cosmic bullets had likely been accelerated by supermassive black holes or colliding neutron stars in galaxies far beyond our own. For the first time, humanity had proof that neutrinos could traverse billions of light years without being deflected by magnetic fields or absorbed by intervening matter, making them pristine cosmic messengers. Yet the real magic happens when IceCube teams up with other observatories. When a high-energy neutrino arrives with a trajectory hinting at its origin, astronomers worldwide scramble to train telescopes on that patch of sky. In 2017, this synergy paid off. A single neutrino led to the identification of a blazar, a jet-spewing black hole, as its likely source, marking the dawn of true multi-messenger astronomy. Now, IceCube isn't just spotting neutrinos, it's helping map the particle accelerators of the universe, from active galaxies to gamma-ray bursts. What keeps scientists shivering on the ice both literally and figuratively are the unanswered questions. Could ultra-high-energy neutrinos reveal the sources of cosmic rays, a century-old mystery? Might they carry traces of dark matter annihilation or exotic physics like magnetic monopoles? With upgrades like IceCube Gen 2, which will expand the detector's volume tenfold, the next decade could unveil neutrinos from the universe's first stars or even relics of the Big Bang itself. Antarctica's frozen silence, once a barrier to exploration, has become a portal to the cosmos. Every blue flicker in IceCube's sensors is a whisper from the void, a reminder that the most profound discoveries often come from learning to listen in the dark. Imagine a universe just out of reach, an invisible twin to our own, separated by dimensions too small to see but vast enough to hide entire worlds. According to string theory, these hidden realms might not be as isolated as they seem, and the key to finding them could be floating through your body right now. Neutrinos, with their bafflingly small masses and penchant for shape-shifting, might be cosmic stowaways slipping between dimensions like whispers through a cracked door. Some physicists suspect their featherweight existence could be a clue that these particles don't just belong to our universe. They're dipping in and out of others, carrying traces of realities we can't yet perceive. The math behind this idea is as elegant as it is mind-bending. In string theory's framework, the universe could have up to 11 dimensions, most curled up so tightly we'd never notice them. But neutrinos, with their interactions, might be sensitive to these hidden folds. Picture a marble rolling across a tablecloth with tiny wrinkles. Its path would wobble ever so slightly, affected by textures invisible to the naked eye. Similarly, if neutrinos are brushing against extra dimensions as they travel, it could explain why their masses are millions of times lighter than other particles. That missing weight might not be missing at all. It could be leaking into other realms, diluting their presence in ours. Even wilder is the possibility that neutrinos from parallel universes are bleeding into our detectors. If alternate versions of our cosmos exist, each with their own quantum rules, their neutrinos might oscillate differently than ours. Experiments like Dune and HyperK and are hunting for anomalies in neutrino behavior, unexpected patterns in how they change flavors or interact with matter. A single statistical blip in the data could be the first faint echo of a multiverse, like finding a letter in your mailbox addressed to someone in a house that doesn't exist on your street. Critics argue these ideas stretch the limits of testability, but the allure is undeniable. If neutrinos really are cosmic diplomats shuttling between dimensions, every collision in a detector becomes a potential handshake with another reality. Future experiments might even spot sterile neutrinos particles that don't interact through any known force except gravity. These phantoms could be messengers from dimensions where the laws of physics play out differently, their very existence rewriting our understanding of reality's boundaries. For now, the multiverse remains a thrilling hypothesis, but neutrinos keep offering puzzles that defy conventional answers. Whether they're revealing hidden dimensions or simply taunting us with quantum mischief, one thing's certain: the universe's quietest particles might be shouting secrets we're only beginning to hear. And if they're really whispers from elsewhere, the greatest discovery in physics could come from learning to listen between the lines. In October 2015, the Nobel Prize in Physics didn't just honor a discovery, it cracked open the rulebook of the universe. Takoki Kajita in Japan and Arthur MacDonald in Canada had spent decades chasing ghosts, and their proof that neutrinos oscillate changing flavors as they travel revealed something earth-shattering. These particles had mass. That single revelation sent shockwaves through physics because, according to the Standard Model, the framework that had guided particle science for half a century, neutrinos shouldn't weigh anything at all. The Nobel Committee called it a historic discovery, but it was more than that. It was a key turning a lock we didn't even know existed. Kajita's work at the Super-Kamiokande and detector in Japan focused on neutrinos born in Earth's atmosphere. When cosmic rays smash into air molecules, they create muon neutrinos that rain down toward the ground. But Kajita's team noticed something odd. Detectors buried deep underground caught fewer muon neutrinos coming up through the planet than those arriving straight down from above. The only explanation: some of the upward-traveling neutrinos had morphed into tau neutrinos mid-flight, slipping past detectors tuned to spot only their original form. It was as if you tossed a blue ball into a tunnel and it emerged red, defying every expectation. Meanwhile, nearly 7,000 miles away, Arthur MacDonald's Sudbury Neutrino Observatory in Canada was tackling the solar neutrino problem. For decades, experiments had detected only a third of the electron neutrinos predicted to stream from the sun's core. Critics wondered if we'd misunderstood how stars work. But MacDonald's team, using a tank of heavy water infused with deuterium, proved the missing neutrinos weren't missing at all. They'd simply changed costumes, oscillating into muon and tau neutrinos on their journey to Earth. When the data finally lined up, it was like watching a magician reveal the trick. The sun wasn't broken, neutrinos were just masters of disguise. The implications stretched far beyond bragging rights. Neutrino oscillation demanded mass, and mass meant the standard model was incomplete. Suddenly, theories that had seemed fringe, like sterile neutrinos or extra dimensions, were back on the table. The discovery also hinted at why the universe is made of matter instead of antimatter. If neutrinos and their antimatter counterparts oscillate differently, they might have tilted the cosmic scales in matter's favor during the Big Bang's first seconds. Today, the Nobel's ripple effect is everywhere. Kajita and MacDonald's work inspired detectors like IceCube and Dune, pushing neutrino research into uncharted territory. Their breakthroughs remind us that sometimes the quietest particles have the loudest things to say, and the next revolution in physics might already be hiding in plain sight, waiting for the right experiment to tease it out. Neutrinos have slipped out of labs and into our collective imagination, becoming unlikely stars of blockbuster films and comic books. Take Star Trek, where starship crews routinely fire neutrino beams to scan alien planets or in more dramatic moments deploy them as weapons. While real neutrinos couldn't slice through a sheet of paper, let alone a Klingon battleship, the idea taps into their eerie ability to pass through anything. Even the Flash, DC's speedster superhero, generates neutrinos when he runs at light speed, a nod to the particle's connection to cosmic velocity. Scientists might cringe at the creative liberties, but there's a silver lining. These portrayals turn an obscure physics concept into something thrilling, sparking curiosity in audiences who'd never crack open a textbook. Then there's Hollywood's love affair with neutrino catastrophes. In the disaster flick 2012, a surge of solar neutrinos supposedly heats Earth's core, triggering apocalyptic earthquakes. The premise is pure fiction. Neutrinos interact so weakly that they couldn't warm a cup of coffee, but the irony is delicious. The same particles that effortlessly ghost through planets are cast as planetary wrecking balls. It's like blaming a breeze for toppling a skyscraper. Yet these plot twists reveal a deeper truth. Neutrinos fascinate us because they defy intuition. Their intangibility makes them perfect MacGuffins for storytellers, symbols of the unknown lurking just beyond our grasp. The real magic happens when fiction nudges reality. When Contact depicted a neutrino message from aliens, it wasn't just poetic license, it mirrored real proposals to use neutrinos for interstellar communication. Their ability to travel unimpeded makes them ideal cosmic couriers, a fact that inspires both scientists and screenwriters. And while Hollywood's neutrino myths might make physicists groan, they serve a purpose. Every time a kid watches The Flash and asks, "Do neutrinos really work like that?" it's a gateway to deeper questions. Perhaps the next great neutrino breakthrough won't come from a lab, but from a teenager who first encountered these particles in a comic book. After all, today's wild sci-fi premise could be tomorrow's thesis topic. When science and storytelling collide, even the smallest particles can leave the biggest impact. Quantum entanglement is one of the strangest phenomena in physics, a bizarre connection where particles become linked across space, instantly mirroring each other's states no matter how far apart they drift. Einstein famously called it spooky action at a distance. a phrase that perfectly captures the unease scientists once felt about this ghostly bond. But what if the universe's ultimate ghost particles, neutrinos, are entangled on a cosmic scale? If neutrinos are indeed Majorana particles, as some theories suggest, their ability to be their own antiparticles could make them perfect candidates for quantum entanglement that spans galaxies. Imagine two neutrinos born in the same supernova explosion, hurtling in opposite directions across the universe. If entangled, a change in one, say, flipping from electron to muon flavor, could instantly influence the other, even if they're separated by billions of light years. It's as if the cosmos is threaded with invisible strings, with neutrinos as the messengers yanking on them. This idea isn't just philosophical speculation. Experiments like the Deep Underground Neutrino Experiment Dune are designed to study neutrino oscillations with unprecedented precision, searching for patterns that might hint at entanglement. When neutrinos from distant sources like supernova or active galactic nuclei arrive at Earth, scientists can analyze their flavors and energies for correlations that defy classical physics. If two neutrinos originating from the same event but arriving at detectors thousands of miles apart show synchronized changes in flavor or spin, it could be smoking gun evidence for entanglement on a scale we've never seen. The challenge is separating these quantum whispers from the cacophony of random neutrino interactions, like trying to eavesdrop on a single conversation in a crowded stadium. But why does this matter beyond the realm of particle physics? If neutrinos can maintain entangled links across cosmic distances, it could revolutionize our understanding of information itself. In quantum mechanics, entanglement is the backbone of emerging technologies like quantum computing and cryptography, where particles act as instantaneous relays for data. Neutrinos, with their ability to zip through planets and stars untouched, could theoretically form a universe-wide network, nature's own quantum internet. Some theorists even speculate that entangled neutrinos might explain how the early universe maintained coherence during its rapid expansion, like invisible stitching holding the fabric of spacetime together. The implications get even wilder when you consider time. If neutrinos are Majorana particles, their entanglement might not respect the usual flow of cause and effect. An event in the present could influence a neutrino state in the past, or vice versa, weaving a web of connections that defies our linear perception of time. It's a concept that bends the mind, suggesting that the universe's hidden wiring might operate on rules far stranger than we've dared to imagine. For now, the hunt for entangled neutrinos remains one of physics' most tantalizing frontiers. Every time a detector catches a neutrino from a distant supernova or a flaring black hole, it's not just collecting data, it's listening for echoes of a quantum conversation that might span the entire cosmos. And if those whispers ever reveal their secrets, we won't just be rewriting the rules of particle physics, we'll be uncovering the universe's most deeply hidden language. Picture a particle accelerator not pointed at a distant target, but aimed straight down through the Earth itself. That's the essence of neutrino beam experiments, where labs like Fermilab in Illinois don't just study these ghostly particles, they manufacture them in controlled bursts, then fire them like cosmic bullets through hundreds of miles of solid rock. The target, detectors like the Deep Underground Neutrino Experiment, Dune in South Dakota, waiting to catch the faintest flicker of a neutrino's arrival after its subterranean journey. It's the ultimate game of quantum pinball, with the planet itself as the playing field. Why go to such extremes? Because Earth makes the perfect filter. When Fermilab's proton beam smashes into a graphite target, it creates a shower of particles, mostly pions and kaons, which decay into neutrinos as they race down a long tunnel. By the time this beam hits the ground and plunges into the planet's crust, every other particle has been absorbed or deflected. Only neutrinos, indifferent to matter's obstacles, emerge unscathed on the other side. It's like trying to send a message through a mountain by shouting and realizing only whispers, the ones you didn't intentionally send, make it through. But the real magic happens during the journey. As these lab-made neutrinos barrel through Earth, they oscillate, shifting between electron, muon, and tau flavors like a chameleon cycling through colors. By comparing the beam's composition at the source to the handful of particles caught at the distant detector, scientists can map these transformations with surgical precision. Each oscillation is a clue, revealing the particles' mass differences and potentially something even more profound, a wrinkle in the universe's symmetry called CP violation. Here's why that matters. If neutrinos and their antimatter counterparts oscillate at different rates, it could explain why the cosmos is filled with matter rather than annihilated into pure energy. The same imbalance might have played out microseconds after the Big Bang, tilting the scales just enough to allow galaxies, planets, and us to exist. Dune's goal is to measure this asymmetry by firing beams of neutrinos and antineutrinos separately, watching for discrepancies in their oscillation patterns. It's like weighing two seemingly identical coins and finding one consistently lighter, evidence of a minting error written into the fabric of reality. The engineering behind these experiments borders on science fiction. Fermilab's neutrino beam starts with protons accelerated to nearly light speed, then smashed into a target so dense it glows white-hot. The resulting particle shower gets focused by a series of magnetic horns, sculpting the chaos into a coherent beam before it dives underground. Meanwhile, Dune detectors giant tanks filled with liquid argon, chilled to -300 degrees Fahrenheit, wait like time capsules buried in a South Dakota mine. Their sensors fine-tuned to spot the ionization trails left by a single neutrino's rare collision. But the surprises have already begun. Early data from similar experiments like Japan's T2K hint at tantalizing anomalies, flavors oscillating in ways the standard model doesn't fully predict. Could these deviations point to sterile neutrinos, extra dimensions, or physics beyond our current understanding? Every pulse of Fermilab's beam is a probe into that unknown, turning the Earth into both a laboratory and a lens. What's striking is how these man-made neutrino highways mirror cosmic processes. The same oscillations we measure in detectors play out in solar cores and supernova remnants, linking controlled experiments to the universe's grandest stages. By bending neutrinos to our will, we're not just solving particle puzzles, we're learning to speak the universe's hidden language, one beam pulse at a time. The next generation of neutrino detectors isn't just an upgrade, it's a revolution. Imagine a vat of liquid argon so pure, so still, that when a neutrino finally, against all odds, collides with an atom inside, the event leaves trails of electrons as precise as ink on paper. That's the heart of Dune, the deep underground neutrino experiment, a colossal undertaking that will fill 4-storied all tanks with 70,000 tons of this ultra-cold liquid buried a mile beneath South Dakota. Unlike older detectors that catch fleeting flashes of light, Dune argon chambers act like three-dimensional cameras, reconstructing neutrino interactions with such fidelity that scientists can practically watch these ghostly particles dance. Every oscillation, every rare collision will be mapped in exquisite detail, offering clues about why the universe favors matter over antimatter and whether sterile neutrinos, those hypothetical heavyweights, are hiding in the shadows. Meanwhile, across the Pacific, HyperK and is taking everything that made its predecessor, Super-K, legendary and scaling it up to jaw-dropping proportions. Picture a cylindrical tank so vast it could house a Boeing 747, filled with 260,000 tons of ultra-pure water. That's HyperK, a detector so sensitive it could spot the decay of a single proton, a process so rare it might take longer than the current age of the universe. But proton decay isn't its only quarry. When the next nearby star goes supernova, HyperK won't just catch the neutrino burst, it'll capture the explosion's heartbeat, tracking fluctuations in the particle flood that reveal the dying star's final convulsions. It's like turning a stethoscope on the cosmos itself. These megaprojects aren't just bigger, they're smarter. Dune liquid argon can distinguish between neutrinos and their antimatter counterparts, a crucial detail for probing one of physics' biggest mysteries, why we live in a universe dominated by matter. HyperK, with its army of 20,000 light sensors, can pinpoint the direction of incoming neutrinos with such precision that it could trace a cosmic ray back to a single galaxy. Together, they form a global network, a silent symphony of steel, water, and argon tuned to the faintest whispers of the quantum world. But the real excitement lies in what they might uncover beyond the expected. Neutrinos have a habit of defying predictions. Their masses, their oscillations, even their very existence once upended entire theories. With detectors this precise, anomalies aren't just noise, they're potential portals to new physics. Could a subtle glitch in neutrino data hint at extra dimensions? Might an unexpected interaction reveal particles lighter than neutrinos, flitting through detectors like quantum fireflies? The next decade of neutrino research isn't just about filling gaps in textbooks, it's about discovering whether those textbooks need a whole new chapter. And the ambition doesn't stop there. Proposed projects like the Pacific Ocean Neutrino Experiment aim to turn entire ocean depths into detectors, while space-based concepts imagine using the moon as a neutrino catcher. Each leap in scale and sensitivity brings us closer to answering questions we haven't even thought to ask yet. The universe has been sending us messages in neutrinos for billions of years. With these next-generation detectors, we're finally building the tools to listen. Neutrinos might seem like unlikely players in the story of life, but these ghostly particles could be silent architects of biology itself. Picture this, as cosmic neutrinos rain down on a planet, their subtle interactions with atoms might nudge the machinery of DNA, introducing tiny mutations over generations. Some scientists speculate that periods of intense neutrino flux, like those from nearby supernova, could accelerate evolutionary change, acting as an invisible force shaping the diversity of life. It's a radical idea that the same particles streaming through your body right now might have once influenced the genetic twists and turns that led to you. But the connection goes deeper. High-energy neutrinos from deep space don't just pass through matter, they occasionally smash into atoms with enough force to trigger nuclear reactions. In the icy moons of Jupiter or Saturn, where subsurface oceans slosh beneath frozen crusts, these collisions could release bursts of energy, churning chemical soups into complex organic molecules. Some researchers even propose that neutrinos might deliver phosphorus, a crucial ingredient for life, to worlds where it's otherwise scarce. Imagine a neutrino striking a molecule on a distant exoplanet, sparking a chain reaction that eventually leads to the first stirrings of biology. The universe's most aloof particles could be its most generous chemists. The implications for astrobiology are staggering. If life on Earth evolved under a constant drizzle of neutrinos, might the same be true elsewhere? On planets bathed in the neutrino glow of active galactic nuclei or pulsars, mutation rates could soar, creating ecosystems unlike anything we've seen. Even more tantalizing, if neutrinos helped deliver life's building blocks here, they might have done the same in other star systems, seeding the cosmos with organic potential. Of course, this is speculative, but that's the point. Neutrinos remind us that life doesn't exist in isolation. It's woven into the fabric of particle physics and cosmic history. Every time we look up at the stars, we're not just observers. We're participants in a universe where the tiniest particles might hold the keys to our biggest questions. And if neutrinos really did play a role in our origins, the search for alien life might need to start by listening to the whispers of the universe's quietest travelers. Right now, the most precise clocks on Earth, atomic clocks, like those used in GPS satellites, keep time by counting the vibrations of cesium or rubidium atoms. But what if there's a way to track time even more accurately, using particles so indifferent to their surroundings that not even magnetic fields or temperature swings can throw them off? Enter neutrinos, the universe's ultimate ghostly metronomes. Because these particles barely interact with matter, they're virtually immune to the environmental noise that can subtly distort atomic clocks. A hypothetical neutrino clock wouldn't just tick with unparalleled precision. It could redefine how we measure time itself. The concept hinges on a simple but profound idea. Neutrinos oscillate between flavors at predictable intervals, like a cosmic pendulum swinging in perfect rhythm. Unlike atomic clocks, which rely on electrons jumping between energy levels, a process that can be minutely affected by external forces, neutrino oscillations are governed by their intrinsic mass differences, a property untouched by the chaos of the world around them. Picture two identical watches, one placed in a storm and the other in a vacuum. The storm might jostle the first watch's gears, but the second keeps perfect time, indifferent to the chaos. Neutrinos are that second watch, ticking flawlessly whether they're passing through a star or a steel wall. The implications for technology are staggering. GPS systems, which rely on atomic clocks to pin down your location, could become exponentially more precise. Right now, even the tiniest drift in satellite clocks can throw off navigation by meters. But neutrino-based timing could reduce those errors to millimeters, enabling self-driving cars to navigate with surgical accuracy or archaeologists to map ancient ruins down to the grain of sand. Deep space missions, where signal delays make real-time control impossible, could use neutrino pulses as ultra-stable beacons, synchronizing probes across billions of miles with the precision of a conductor's baton. Yet the real promise lies in fundamental physics. Neutrino clocks could test Einstein's theory of relativity with unprecedented rigor. If time flows differently under strong gravity, as general relativity predicts, comparing a neutrino clock on Earth to one in space might reveal subtle discrepancies no atomic clock could detect. Some theorists even suggest that neutrino oscillations could serve as a probe for quantum gravity, bridging the gap between the subatomic world and the cosmos. It's like discovering that the universe has been quietly tapping its foot to a rhythm we're only now learning to hear. Of course, building such a clock is easier said than done. Current neutrino detectors are warehouse-sized behemoths that catch maybe a handful of interactions per day. Scaling that down to a practical device would require breakthroughs in neutrino sources and sensors, perhaps using ultra-cold materials or quantum dots tuned to neutrino vibrations. But the same was once said of atomic clocks, which once filled entire labs and now fit on microchips. The irony is delicious. Particles that once seemed too elusive to study might become the bedrock of our most precise technologies. From guiding rockets to testing the fabric of spacetime, neutrino clocks could turn the universe's quietest particles into its most reliable timekeepers. And if that future arrives, we won't just be keeping time, we'll be listening to the universe's own heartbeat. Building the tools to catch neutrinos isn't just a scientific challenge, it's a moral one. Take the IceCube Neutrino Observatory, a detector buried in Antarctic ice that cost over $270 million to construct, or the upcoming deep underground neutrino experiment, with a price tag pushing $1.5 billion. In a world where that same money could vaccinate millions, build sustainable infrastructure, or fund renewable energy projects, it's fair to ask, are we justified in spending so much to study particles that barely interact with anything? The debate cuts to the heart of what society values most: immediate human needs versus the long-game pursuit of knowledge. Yet history offers a compelling counterargument. When CERN scientists developed the World Wide Web in the 1980s, it wasn't because they set out to revolutionize communication. They simply needed a better way to share particle physics data across labs. GPS, MRI machines, even the touchscreen on your phone, all emerged from fundamental research that initially seemed disconnected from daily life. Neutrino science has already spawned breakthroughs like ultra-sensitive radiation detectors for nuclear safety and medical imaging techniques that could one day spot tumors earlier than current technology allows. The irony is profound. The most abstract science often yields the most practical innovations, but only if we're willing to invest without demanding immediate returns. Critics argue that neutrino research is a luxury humanity can't afford in an age of climate crises and inequality. Why drill into glaciers or fill underground caverns with liquid argon when rising seas threaten coastal cities? But proponents see a false dichotomy. The same cutting-edge engineering that builds neutrino detectors also advances geothermal drilling technology, improves cryogenic storage for renewable energy, and refines materials science for sustainable construction. Japan's Super-Kamiokande, for instance, pioneered ultra-pure water filtration systems now used in disaster relief to provide clean drinking water. The line between pure and applied science blurs when knowledge spills over into unexpected domains. The tension reflects a deeper question. How do we measure the value of curiosity? When the ancient Greeks tracked the motions of stars, they weren't solving hunger or disease, yet their observations laid the groundwork for navigation, agriculture, and modern physics. Neutrinos might seem esoteric today, but their secrets could unlock nuclear fusion, revolutionize quantum computing, or reveal why the universe exists at all. The gamble is that by chasing ghosts, we'll stumble upon light. Perhaps the real ethical failing would be short-term thinking. Great civilizations are remembered not just for how they fed the hungry, but for how they fed the human spirit. The pyramids, the telescopes, the particle colliders that asked, what else is possible? Neutrino detectors are cathedrals of the invisible, built on faith that understanding the cosmos ultimately serves Earth's inhabitants too. The challenge isn't choosing between survival and discovery, but recognizing their threads of the same tapestry. After all, the same particles streaming through your body right now have stories to tell about supernova, the Big Bang, maybe even the future. The only question is whether we're willing to listen. In a Tokyo gallery, a darkened room pulses with streaks of blue light, each flash tracing the path of an invisible neutrino detected by the Super-Kamiokande and Observatory. This isn't a physics lecture, it's an art installation by Japanese Collective Team Lab, translating trillions of ghostly particles into a shimmering dance of lasers and sound. Across the globe, similar projects are turning neutrino science into sensory experiences, from Icelandic composer Jóhann Jóhannsson's orchestral piece based on cosmic ray data to Argentinian artist Tomás Sarasno's suspended sculptures mimicking particle collisions. These works don't just represent neutrinos, they invite us to feel their mystery in our bones. What drives artists to obsess over particles they'll never see? The answer lies in the shared frontier of art and science, the hunger to make the intangible tangible. When physicist Arthur MacDonald wanted to explain neutrino oscillation to the public, he partnered with glassblowers to create swirling, color-shifting sculptures, each hue transition mirroring a neutrino's quantum metamorphosis. The result wasn't just educational, it was hypnotic. Like a painter capturing wind by its effect on grass, these artists render neutrinos visible through their cosmic fingerprints. This fusion of disciplines does more than decorate data. It rewires how we perceive scientific discovery. Consider the neutrino drawing chamber at CERN, where visitors wield magnetic pens to sketch paths inspired by real particle tracks. The act of drawing becomes a dialogue between intuition and evidence, blurring the line between hypothesis and imagination. It's no coincidence that many groundbreaking scientists, from Einstein to Feynman, credited artistic thinking, visualization, pattern recognition, metaphorical leaps as key to their breakthroughs. A child mesmerized by a neutrino light show today might design tomorrow's revolutionary detector. The irony is delicious. Particles that refuse to interact with matter have sparked some of humanity's most collaborative endeavors. When photographer Catherine Yass submerged cameras in water tanks to recreate Cherenkov radiation, she worked alongside Oxford physicists to calibrate each shot. The resulting images, glowing like submerged stars, adorn both museums and quantum mechanics textbooks. This synergy challenges the tired trope of two cultures divided. Art and science aren't opposing forces but twin lenses focusing on the same cosmic wonder. Perhaps that's why neutrino art resonates so deeply. In a world saturated with visible stimuli, these works train us to cherish the unseen architectures of reality. Every sculpture, soundscape, or hologram whispers the same revelation. The universe is far stranger and more beautiful than our eyes alone can witness. And in that space between the measurable and the imagined, curiosity takes flight. Neutrinos have been teasing scientists for nearly a century, dangling answers just out of reach before vanishing into the quantum fog. Take their mass. Why do particles so insubstantial weigh anything at all? The Standard Model, physics' most successful theory, predicted they'd be massless, yet experiments proved otherwise. That tiny weight, 1,000,000 times lighter than an electron, is like finding a feather that somehow tips a freight scale. Some theories suggest neutrinos borrow mass from hypothetical Higgs-like fields, while others propose their heft leaks in from extra dimensions. Every time researchers narrow the possibilities, neutrinos reveal another layer of complexity, as if the universe is playing a cosmic shell game with the rules of reality. Then there's the Majorana mystery, the tantalizing possibility that neutrinos are their own antiparticles. If true, it would mean these particles are essentially quantum phantoms, flickering between matter and antimatter like a light switch toggling itself. The implications would ripple across cosmology, potentially explaining why the universe didn't annihilate itself in a blaze of matter-antimatter collisions after the Big Bang. Experiments like Quore, buried under an Italian mountain, are hunting for a rare nuclear decay that could confirm this. Picture a vault of crystals chilled to near absolute zero, waiting years for a single telltale vibration, a whisper that neutrinos are cosmic magicians, pulling reality from their own quantum hats. But the puzzles don't stop there. IceCube's detection of ultra-high-energy neutrinos, some with energies 1,000 times greater than particles in the Large Hadron Collider, has astronomers scrambling. These cosmic bullets don't match any known sources. Are they forged in the jets of supermassive black holes? Born in the wreckage of colliding neutron stars, or could they be the decay products of hypothetical dark matter particles, finally revealing the universe's hidden scaffolding? The frustration is palpable. Every time a detector catches one of these extreme neutrinos, its path points back to empty sky, as if the universe is scribbling clues in invisible ink. The most exhilarating part, neutrino research thrives on failed predictions. When the mini-BUENI experiment at Fermilab saw more oscillations than expected, it sparked rumors of sterile neutrinos, a fourth flavor that interacts only via gravity. When reactor neutrino counts came up short, theorists dusted off ideas about quantum decoherence in extra dimensions. Even anomalies that later get debunked, like the faster-than-light neutrino scare, push technology forward, forcing detectors to become impossibly precise. It's a reminder that in physics, the wrong answers often lead to the right questions. What's next? A supernova in our galactic backyard could flood detectors with neutrinos, offering a real-time look at stellar death. A glitch in Dune neutrino beam might reveal cracks in the standard model, or perhaps a theorist scribbling equations at midnight will stumble on a connection no one else saw. The only certainty is this: neutrinos won't surrender their secrets easily. They've spent 14 billion years as cosmic enigmas, and they're not about to start making sense now. Every flicker in a detector, every statistical blip, is a dare from the universe, a challenge to rethink not just particles, but the very nature of existence. And that's what makes the chase so irresistible. Imagine a world where everything you see, touch, and feel, every mountain, every drop of rain, even your own hands, amounts to less than 5% of what's actually out there. That's not science fiction. It's the startling truth modern physics has handed us. Neutrinos, those phantom particles streaming through your body right now, are part of a vast, invisible tapestry that makes up the majority of the universe. Alongside dark matter and dark energy, they force us to confront a humbling question. Is our entire understanding of reality just a flickering candle in an endless cosmic dark? Philosophers have wrestled with the nature of reality for millennia, but neutrinos add a twist even Plato couldn't have imagined. If the most abundant particles in the cosmos barely interact with matter, what does that say about the solid world we take for granted? Think of a subway station at rush hour. The people are like atoms, bustling and colliding, while neutrinos are the unnoticed breeze slipping effortlessly through the crowd. The subway looks real because we're part of the chaos, but the breeze, indifferent and everywhere, might be closer to the universe's true nature. This challenges the very idea of objectivity. Science traditionally relies on observation and measurement, but how do you observe something that leaves no trace unless it chooses to? Neutrinos flirt with detection, appearing only when they want to, like a detective forced to solve a crime where the suspect is invisible and the evidence evaporates instantly. Some philosophers argue this makes neutrinos a perfect metaphor for the limits of human knowledge. We build elaborate detectors to catch glimpses of them, yet their full nature remains just out of reach, a reminder that reality might be far stranger than our tools can reveal. And then there's the existential kicker. If most of the universe is invisible, undetectable, or barely interacting with the matter we're made of, can we even call ourselves its true inhabitants? Or are we just temporary residents in a house built for ghosts? Neutrinos don't care whether we perceive them. They've been here since the Big Bang, outlasting stars, planets, and civilizations. Their indifference is a cosmic lesson in humility. For all our telescopes and colliders, we're still decoding a universe that operates largely without us. Yet there's a beauty in this uncertainty. Neutrinos force science and philosophy to dance together, each step revealing new questions. Maybe the unseen isn't meant to be fully grasped, only wondered at. After all, the ghosts aren't just in the machine, they are the machine, the silent architects of a reality we're only beginning to sense. And in that tension between what we know and what we can't yet see, there's room for both awe and discovery. You don't need a PhD or a particle detector to dive into the world of neutrinos. Some of the most groundbreaking discoveries start with ordinary curiosity. Platforms like Zooniverse's Neutrino Watch let anyone with an internet connection sift through real data from experiments like IceCube, tagging cosmic events that might signal high-energy neutrinos. It's like being handed a magnifying glass to search for stardust in a digital haystack. Volunteers have already helped identify unusual particle tracks that algorithms missed, proving that fresh eyes can spot what machines overlook. Museums are bringing these ghostly particles to life in ways that defy expectations. The Science Museum in London features a cloud chamber where visitors can watch cosmic rays, neutrinos' higher energy cousins, streak through vapor trails in real time. Meanwhile, Tokyo's Muricon pairs Super-Kamiokande and neutrino data with immersive light projections, turning abstract physics into a sensory experience. Even local planetariums are joining in, with shows that trace neutrinos' journey from the Big Bang to your backyard. These exhibits don't just explain science, they let you feel it, bridging the gap between theory and wonder. For those who prefer learning on the go, podcasts like the Neutrino Diaries or Physics Frontiers break down complex concepts into bite-sized stories. Imagine hearing about a supernova's neutrino burst during your morning commute, or how detectors use ancient Roman lead to shield against background radiation. Some episodes even feature researchers sharing their eureka. Moments like the time a faulty freezer almost derailed a Nobel-winning experiment. These stories humanize science, reminding us that every discovery begins with someone asking, "What if?" The most exciting part, you might contribute to the next breakthrough. Amateur astronomers have spotted supernova before professional surveys. High school students have co-authored papers on galaxy classifications. With neutrino science expanding faster than ever, the next big clue could come from a classroom, a coffee shop, or your couch. All it takes is clicking a dataset, visiting an exhibit, or simply wondering aloud. After all, the universe doesn't care who unlocks its secrets, only that someone keeps trying. Neutrinos aren't just passing through you unnoticed, they're rewriting the rules of reality as they go. These ghostly particles have already shattered our assumptions about mass, matter, and the fundamental forces that shape the cosmos. But what makes them truly extraordinary isn't just what we've discovered, it's how much remains hidden in their quantum whispers. Every time a neutrino detector catches one of these elusive particles, it's not just collecting data, it's intercepting a message from the universe's most extreme environments, stamped with the fingerprints of processes we're only beginning to understand. Consider this: the neutrinos reaching Earth today began their journeys under circumstances we can barely imagine. Some were forged in the 15 million degree heart of our Sun, where hydrogen atoms fuse under crushing pressure. Others fled the collapsing core of a dying star, outracing the supernova's light by hours. A select few may even be relics from the Big Bang itself, cosmic time travelers carrying secrets from the universe's first second of existence. Each flavor, each oscillation, each rare interaction tells part of a story that spans billions of years and countless light years. A story we're piecing together one detector flash at a time. The revolution isn't slowing down. Next-generation observatories like HyperK and Dune aren't just upgrades, they're quantum leaps in our ability to listen to the universe. HyperK's colossal water tank will catch neutrino interactions with such precision that it could spot a supernova's neutrino burst from the edge of the observable universe. Dune liquid argon chambers might finally prove whether neutrinos are their own antiparticles, a discovery that could explain why anything exists at all. These experiments are more than machines, they're time machines, letting us witness cosmic events that shaped the very atoms in our bodies. Yet for all our technological marvels, neutrinos keep defying expectations. The same particles that helped confirm how stars shine are now hinting at physics beyond the standard model: extra dimensions, sterile neutrinos, or quantum entanglements spanning galaxies. They challenge us to think bigger, dig deeper, and stay humble in the face of nature's complexity. When researchers at IceCube traced a single high-energy neutrino back to a flaring black hole 4 billion light-years away, they didn't just solve a mystery, they opened a new window on the universe, one where invisible particles illuminate what light cannot. So the next time you step outside and feel the sun's warmth, remember this: you're also bathing in an invisible rain of solar neutrinos, each one a direct messenger from our star's fiery core. When you look up at the night sky, know that ghostly particles from distant supernova and colliding galaxies are streaming through your eyes. We're all walking neutrino detectors, immersed in a cosmic conversation that began at the dawn of time. The detectors we build, the theories we test, they are our way of learning the language. And as the next chapter of this quantum detective story unfolds, one thing becomes clear: the universe's quietest particles have the loudest